Okay, so now we're going to look at some results of intermolecular forces. Surface tension, viscosity, and capillary action. So first, surface tension. My husband actually loves to tie flies. So here's a trout fly. There's a fishing line. There's a metal hook in here. What do metal things usually do when you toss them in water? They sink because they're more dense than the water. But this trout fly can float on top of the water. Other things can do this as well. Here we've got a paper clip floating on water. You can try that at home. If you want to do it, I'll give you some tips. You can float a needle. You maybe have seen water skaters, these little bugs, and they walk around on top of the water. How do they do that? Surface tension. So surface tension is the tendency of liquids to minimize their surface area. We talked about that round glob of water, that sphere of water in space. Why did it make a sphere? Because of the attraction of the water molecules to each other. They want to maximize that attraction, and so they do that by minimizing the surface area. Surface tension can be quantified. It's measured as the energy required to increase the surface area by some unit amount. Water has a surface tension of 72.8 millijoules per square meter. Probably means next to nothing to you. That's okay. So how does this work? Well, here we have a diagram of molecules in a liquid. At the surface, a surface molecule can interact with molecules next to it on the surface and with some that are on the interior. And so as this picture is drawn, we've got this surface molecule interacting with 4 neighbors. Molecules in the interior can interact with more. So this one can interact with 6 neighbors. And of course, this is just a 2-dimensional slice. It would be different if you went 3-dimensional. So this molecule on the surface has higher potential energy. It's less stable than the ones on the inside. If we want to increase the surface area of this liquid, maybe to put something into it that would increase the surface area, we're going to have to push some of the water out of the way, right? And that's going to mean that a bunch of molecules that were on the interior are now on the surface. It doesn't like to do that because that increases potential energy. So liquids tend to minimize their surface area. There's that drop of water again. This is a picture of a spider web. Now this is on Earth, but those droplets are small enough that gravity's not having much an effect on them. And they're perfect little spheres. The reason it forms spheres is due to the surface tension. As you increase the strength of the intermolecular force, the surface tension increases. If you decrease the strength of the intermolecular force, the surface tension decreases. So you can float a paperclip on water. You cannot float a paperclip on gasoline because it's nonpolar and it does not have strong intermolecular forces. It has much lower surface tension. Any questions? I would not recommend trying to float a paperclip on gasoline. Could be hazardous. Another property is viscosity. Viscosity is the resistance of a liquid to flow, kind of how thick it is. You think about honey or good maple syrup, and you pour it, and it pours slow, right? It's like thick compared to water. It's more viscous. Viscosity is measured with a unit called the poise, which is 1 gram per centimeter second. Awesome. We've got these numbers here. That's all we're going to do with the poise. If you have stronger intermolecular forces, you have more resistance to flow. So the viscosity is greater. So if you have a larger molecule, you're going to have larger dispersion forces, and you're going to have larger viscosity, higher viscosity. Here we're looking at straight chain alkanes, pentane, hexane, heptane, octane, nonane. The molar mass increases. There's their formulas. The viscosity increases from 0.2 up to 0.7. Larger dispersion forces. Any questions? Viscosity does depend on temperature. Because at higher temperatures, the particles on average have more kinetic energy, and so they are more able to overcome the stickiness of the adjacent molecules, and they can flow more freely. So here we're looking at water, the viscosity of water. At 20 degrees, it's 1 centipoise, and at 100 degrees, it's 0.2. So water is more fluid at higher temperatures. This is of great importance for things like motor oils. The oil in your engine needs to be of a particular viscosity. You don't want it so thick that it's not going to flow into all the crevices that it needs to be in, but you don't want it too thin because then it's going to fall down and just stay at the bottom, and it's not going to coat things. And so you want this balance. Well, in the old days, you used to have to change your motor oil because in the summer, it would get too thick if you didn't change it. It would get too thin. And in the winter, it would be too thick. And so you had to change the grade of motor oil that you put in there. Now they have really cool polymer oils that unwind at higher temperatures. So this has to do with the shape of a molecule. So a long, stringy molecule has more surface area, and so it's going to have higher viscosity than one that's all coiled up in a ball. So at high temperatures, they unwind and become stickier. And so the viscosity doesn't change very much. When things get cold, they coil up, reducing the viscosity. And so now you can have one motor oil that'll go from 10 to 40 instead of having to change it. Another one is capillary action. So here we have someone getting a finger prick, and the blood wells up, and then you can put a capillary tube here, and the blood will just rise up into the capillary tube. No suction or anything, just goes up there. Is that magic? No. Capillary action is the ability of a liquid to flow against gravity up a narrow tube. So there's two forces at work here. There are cohesive forces, the forces that attract the molecules to each other, and there are adhesive forces, the attraction between the liquid and the surface of the tube. If the adhesive forces are stronger, the liquid will rise. So what happens is, well, let's look at this one maybe. So here are different diameters of tubing, and the thin tube, the liquid will rise much higher than in a fat tube. But what happens is the molecule is attracted to the glass, and so it creeps up a little bit. But it also has cohesive forces that keep it attracted to what it left behind, and so essentially it's creeping up the wall. It's drawing itself up the wall in opposition to gravity. And so if it's very narrow, like this one, it has less to support. Those adhesive forces have less to support, and so they can go higher than if you've got a really fat tube. Questions? Another aspect of capillary action has to do with the meniscus. So here is water in a test tube, and we've seen this a lot in lab. There's a meniscus. There's a curve. It almost looks like a contact lens sitting on top of the liquid. And for aqueous things, where water is the solvent, it curves down. And so we always measure to the bottom of the meniscus. This is concave because the adhesive forces that pull it up the sides are stronger than the cohesive forces that hold it together. If you look at mercury in a tube, which would be fun, but we can't let you play with it, we see that the meniscus goes in the opposite direction. That's because the cohesive forces of mercury atoms attracting each other, that's greater than the adhesive forces. And so it actually bulges up in the middle. It's trying to make a sphere there. It is not attracted to the glass. Water's attracted to the glass and it will creep up. Now what the tube is made out of is going to have a big impact. There are some plastics that water is not attracted to, and so you can see a flat meniscus. There's no curve at all. Any questions?